So in this video we're going to review the calculations in exercise 33 of your maths book, and we'll start with question 1, which, if we have a look at it, is clearly a question about enthalpy changes. And so what we're going to do is break down the question and have a think about what we would need to do first. So we have got a student carries out an experiment to measure the enthalpy change of combustion of hexane. So the combustion is burning hexane in oxygen. The student finds that the combustion of 1.29 grams of hexane, so they're burning 1.29 grams of hexane underneath a beaker of water, and 200 grams of water rose from 20.5 degrees C to 65.5 degrees C. They've given us the value of C. That usually gives us a clue that we might need to use that calculation with C, Q equals MC delta T, and they want us to find the enthalpy change in kilojoules per mole and give our answer to an appropriate number of significant figures. So while we're here, let's have a think what that might be while we've got all the data in front of us. So we've got 1.29 grams, 3 significant figures. 200 grams, that one is not so clear because that could be 1, 2 or 3 significant figures, all of which would be exactly 200 grams. 20.5 and 65.5 and 4.18, everything else is 3 significant figures. So I'm going to say that we're going to go for 3, appropriate number of significant figures. So here we go, it's a little diagram. We're burning our hexane underneath our beaker of water. So this is our 200 grams of water. And we measured that temperature on that thermometer. Our hexane's down here in our spirit burner. So Q equals MC delta T. How much did the temperature rise? So our first mark is for putting the numbers into this equation. We need to find the temperature rise, 45 degrees, by doing the difference. Doesn't matter that they're in degrees C, because the temperature difference in both degrees C and Kelvin will be identical. And put that into our Q calculation. So the thermometer measured the temperature rise of the water. So this number here is how much the water rose. So the mass needs to be the mass of the water. And this is the specific heat capacity of water. So 200 times 4.18 times 45. And because 4.18 is in joules per Kelvin per gram, this is going to be in joules. So it's really important that you understand the units. So this would be a mark here. What you need to do now is work out how much hexane it took to make that energy change. So I've got mass over MR. Because it's C6H14, I can add up the MR. And then I can work out the number of moles. So you give yourself another mark for that. And then you remember that if I want to work out how many kilojoules per mole, I'm going to take this number that's in joules. First of all, I'm going to turn it into kilojoules. So this times 10 to the minus 3 is turning it into kilojoules. And divide by the number of moles. Do you remember what this minus is about? This minus here is about the fact that the temperature rose. It was an exothermic change. So at the moment we've got our answer. Here we've done the correct calculation. We can give ourselves another mark, but this isn't the final answer because the question said appropriate significant figures. So if we want to give this to 3, which was what we decided, then minus 2,508. We've got things in the thousands, the hundreds, the tens and the units, but 3 significant figures would be in the thousands, the hundreds and the tens. So basically we're being asked to round this to the nearest 10, and that would be minus 2,510. 3 significant figures. Okay. Question 2 then had a look at more enthalpy change questions. We had 4 values for different fuels, and the first 3 were plotted on the graph. So there we are, we had a little graph, and it asked us to plot that value for butane. So the first thing we need to do is work out the formula of butane, which, since but is 4 and it's an ane, it's 2n plus 2 hydrogens, and then we can work out the MR, which is 58. And 58 is found on our graph here. So on this scale from 40 to 60, there's 58. So what we're going to do is plot a point at 58 and the value from the table, minus 2,877. So we want to looking at going down from 58, down, and on this scale, 2,000 900 would be just one line up, so just before there we're going to plot that point. So give yourself a mark if you plotted that point at 58 and minus 2,877. And then it says use it to work out for pentane. Show any working that you've done. So what we'd be looking for on this is, did you work out that pentane had, so I've just drawn a line of best fit through it first, but did you work out that pentane was C5H12 and had an MR of 72? So I needed my line to extend as far as 72. So I'm going to then draw a line down from 72 and across. Now I'm coming out at minus 3,500, but there will be a bit of give or take here depending on how your line of best fit looks. So maybe, you know, between 3,400, 3,600, and then read off that number. I got minus 3,500, like I said. But the question was, work out the energy release. Now energy is Q, so I need to work backwards. I need to find out how many moles I had, so mass over MR again, and work out that Q is delta H times moles. So I've got 87.5, or maybe something up to 90 or down to 85, depending on what value of delta H you got. And then the question continues here with a table of data, and they're wanting you to apply Hess's law now. So we've got the enthalpy of combustion of cyclohexane, and we've got this data. So the first thing we need to do is pay attention to the fact that this is formation data, and remind ourselves what formation means. It's the standard enthalpy change when 1 mole of the compound, so when 1 mole of this, C6H12, is formed from the elements, from carbon and hydrogen. And this value is about 1 mole of CO2 being formed from carbon and oxygen. And this value is about 1 mole of water being formed from hydrogen and oxygen. The first thing I'm going to do is try to construct a cycle. So I've put the equation that we're being asked about across the top, and then the elements from which all those things are made across the bottom, because these were formation data. So I formed it from carbon, hydrogen and oxygen, and I balanced the numbers from one side or the other, but it will work with both. And the arrows are going to point up because we're forming these things across the top from these elements at the bottom. We're trying to calculate this top value. We will have information for these two. So let's add up the arrow delta H1, which is pointing at 1 cyclohexane and some oxygen. Now we've got a value for 1 cyclohexane. The 9 oxygens haven't changed, so that's just 9 lots of nothing happening there, so I don't need to add that on. Arrow 2, I'm forming 6 lots of CO2, so 6 lots of the value for CO2, and 6 lots of water, so 6 lots of the value for water, and that is the total for arrow 2. So how would you work out this one? So according to Hess's law, it doesn't matter whether you go the direct route like that, which is just our arrow delta HC, or our indirect route like this, which would be down this the wrong way, so minus arrow 1 plus arrow 2, minus arrow 1 plus arrow 2, put the numbers in and work out an answer. There'll be 3 marks for this. If you construct the correct cycle, you will get 1. If you don't construct the correct cycle, you would have to write an appropriate mathematical expression with sigmas in, which is a bit more tricky, but you would have to say delta HC is the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. I would rather you learn how to construct a cycle. 1 mark for your calculation and 1 mark for the correct answer. Look back at the other part of the question. We've got a number of moles of calcium oxide and a concentration of hydrochloric acid, and we're being asked what volume is needed. So the number of moles of calcium oxide was given to us, but the question is about hydrochloric acid, so we need to know how many moles of hydrochloric acid we've got, and the ratio is 1 to 2, so we need to double it to find the number of moles of hydrochloric acid. And then volume is moles over concentration, so we take those moles and we divide by the concentration, but notice that that's in decimeters cubed, so this won't score a mark on its own because the question asked for it in centimeters cubed. So we need to times by 1,000, and we've got 20 centimeters cubed. So there's just 2 marks for that, 1 for this number of moles and 1 for this volume. Another quick one in question 4. How many electrons are removed from this many grams of neon atoms to form neon? 1 plus. So basically the equation we'll be looking at here is first ionization energy. Neon becomes Ne++ an electron. So every neon loses 1 electron. First thing we need to do with the mass and a formula is work out moles. So I've got the number of moles of neon here. And the question is about electrons. So if I've got this 1 mole of neon, I've got 1 mole of electrons. If I've got 1 times 10 to the minus 3 of neon, then I've got the same number of moles of electrons. But it's how many electrons, and this is Avogadro's constant, which is how many are in 1 mole. So I'm going to times these two together and get this number. So it's 1 mark for the mass over MR calculation and 1 mark for multiplying that answer by Avogadro's constant. Again, another quick moles calculation. These are all from amounts of substance, these last few. So we've got 8 grams of silicon tetrachloride here, and we're being asked how much silicon is made, given that the percentage yield is 90%. So first thing is get yourself a mark straight away, work out moles of silicon, tetrachloride, so 8 over 170.1. The question is actually about silicon, so what's the ratio? And the ratio is 1 to 1. If it was 100% conversion, then we would expect 0.047, but it's actually only 90% conversion, percentage yield of 90, so we're only expecting 0.0423. Now you could do the 90% right at the very end once you've got masses if you like, so these final 2 steps are interchangeable. I've worked out the 90% first and then applied masses Mr. Moles to get 1.2 grams. I've gone for 2 significant figures because the numbers up here is 2 significant figures. But if you'd have taken 0.047 and then times by 28.1 to get mass of silicon and then worked out 90% afterwards, you would still get the exact same answer and it would still be completely correct. You would have all the marks. You've just applied the 90% afterwards. That's fine. Question 6 is a bond enthalpy question. So whenever you get a bond enthalpy question, the first thing you need to do is draw it out. So draw out the bonds. Have a look at that data you've been given, and we're being asked about this bond here. So I've added it to my table with the value x. And then I've reminded myself of the calculation. Bonds broken minus bonds formed. We were given the answer is minus 9 on the previous, in the question on the previous slide. So minus 9 is the sum of the bonds broken, 1 HH and 1 HI, minus the sum of the bonds formed, 2 lots of my unknown. Then I'm just going to apply the algebra, work it out, and get an answer for x. So there'll be 1 mark for this equation here, like there'll be a tick there, 1 mark for your expression you're working, and 1 mark for your final answer. And then the final question in this section is a Kc equilibrium question. A little bit more going on in this than the last few. So it's been broken down for us a little bit, but we've got all this information, and the first thing it asks us to do is write an expression. So remember that Kc is products over reactants, and it must be in square brackets because it's Kc for concentration, and these stoichiometry numbers become the powers. So products SO3 squared over reactants SO2 squared times oxygen, and then work out the units. We've got 2 concentrations on the top and 3 on the bottom. So we've got an extra 1 on the bottom because we can cancel these 2, which is concentration terms to the minus 1. So that's moles to the minus 1, dm to the plus 3. So there would be there 2 marks, so 1 for that and 1 for that. Now the question is actually asking us to find the value for the number of moles of SO3 in the mixture, and we've been given moles of these 2, but the calculation needs concentration, so our first job is to work out the concentrations from the moles. Concentration is moles over volume, making sure the volume is decimeters cubed. So the first thing you do is you get a mark for both of those concentrations. You have to actually work out both of those for that mark. So if you forget to do this, you wouldn't lose all the marks, but there's 1 mark for converting to concentration. If you then rearrange the expression, so that you have SO3 squared, you'll see that it's Kc times SO2 squared times O2. You could get rid of the squared and square root all of this at this point, but I'm going to actually work it out like this so that I don't have to worry too much about brackets and things on my calculator. I'm going to put the numbers in. We were given this, we've worked out these two, and we get this answer. Now, if you've forgotten to do these concentration things here, you won't lose all these marks. You will still get a mark for putting it correctly into this expression here with the moles by accident, but that would be it. You would just get the 1 mark for rearranging, essentially. So I worked that out, and then I square rooted it because that was SO3 squared and I wanted SO3, but this isn't the final answer because this is the concentration of SO3 and the question wanted moles. To work out moles, we have to do volume times concentration. So we're sort of doing the reverse of this step up here, and we get 2.45, and it wanted it to the appropriate number of significant figures, which in this case was 3. So there's a mark there. Remember, there was a mark for our rearrangement here. If you correctly work out your concentration, then obviously you're going to get another mark here.